Welcome to the next lecture in the series Bridges to the Future. Today we'll discuss bridge ancillary components. The modern bridge is not only the structural elements themselves, such as spans, pillars, and abutments. There's also a lot of additional components that are to ensure the safety and comfort of users, as well durability and reliability. It can be pavement, barriers, expansion joints, bearings, those are modern electronic monitoring systems, or even the so-called smart bridges. Uh, we will start today with pavements and waterproofing, the sewage system, railing and barriers, expansion joints and mirrors, approach slabs, and finally inspection and monitoring systems with introduction to the so-called smart bridges. Let's start with the surface and associated surface pavements and associated classification of the types. First of all, the pavement depends on the function of the bridge. So we have road pavement and rail tracks. On road bridges, we have asphalt and concrete pavements, and definitely asphalt is the most common. On railway bridges, we have rail tracks, which can be based on cross beams or track bed with ballast aggregate, and also ballastless tracks. Road surfaces, road pavements, are mainly bituminous materials. They consist of primarily of aggregate, about 90%, binders, about 5%, and mineral filler, around 5% also. It is all mixed in specialized asphalt factories, often mobile, created, constructed locally in the construction area of some motorway section, just to reduce transport costs. On the right side, you can see the asphalt surface borehole, which is supplied in this form to the laboratory testing of the pavement quality. Bituminous surfaces are divided depending on how they are built. Therefore, hot or cold laid surfaces can be used. Definitely the most commonly used are hot laid pavements. We include here asphalt concrete, which is also called a dense graded mix, macadam mastic asphalt, also called as goose asphalt. SMA, known as stone mastic asphalt, this is the gap grade mix, sand asphalt, and popcorn mix, which is also uniform graded mix, and finally drain asphalt, which can remove also water. So we see a lot of types and solutions that are continually changing, and a lot of is happening in this area, especially when looking for surfaces that may be able to recover energy or even reduce the noise in the future. Of course, we are talking here about road surfaces outside the bridge, which doesn't have to be doesn't have to apply to the bridge. Here are some specific working conditions of the pavement, resulting, for example, from the fact that the range of deformations because of bending bridge span is more significant. When it comes to cold laid surfaces, they are mainly used for quick repair or damage, so we have maintenance mix and coarse cold asphalt using cold recycling. Three types of bituminous surfaces are most commonly used on bridges. SMA, known as stone mastic asphalt, which is widely used in Poland. It is high resistance to rotting and extremely durable. Next is asphalt concrete, which is a mix out of stones, bitumen, and pores filled with air. And finally, mastic asphalt, made as a mixture of bitumen, fingered aggregate, and fines that can be also used for waterproofing and in industrial applications. Here we can see the differences in road pavement layers of bituminous materials on the road, beyond the bridge, and just on the bridge. So we have base layers and two asphalt layers with bonding layer and wearing course. It looks similar on the bridge, but besides, we have here a layer of waterproofing and slightly different thicknesses of asphalt layers laid on it. As for the pavement surfaces, it is usually because the pavement are located on the outer edges of the bridge that they are connected with the cornice, barrier and balustrade. Here's an example of monolithic solution. And here's the version with a precast cornice made of polymer concrete, which has recently been very often used in on Polish bridges. Now we'll discuss railway surfaces. To start with an old solution that should no longer be used, it is an open deck or open tracks. You will meet them on many old bridges where the rail is attached to the so-called traverses in the form of large wooden beams. Track bridges with ballast through and ballast bed are most commonly used on new bridges today. It allows ensuring similar comfort conditions for trains crossing the bridge to those which prevail on the route outside the bridge. There is also less noise and better vibration damping. Pretensioned railway sleepers are used for this. These sleepers are protected in this way against the transmission of vibrations from the train to the surrounding area with special anti-vibration pads. Ballastless surfaces with different rail fastening methods are also increasingly used today, either directly to the deck structure or in the channels of particular precast reinforced concrete slabs with vibro-isolation, or even in individual concrete blocks that have different heights to ensure the right track inclination. Here's an example of such a prefabricated panels with channels for fastening rails. The next element in is the deck waterproofing. Most often we use heat-welded roofing felt with increased resistance to dynamic loads and more exceptional durability than those used on the roofs of buildings. Besides, elastomeric or silicone membranes are also used. Here we see a way of laying heat-sealable roofing felt on the deck, and here a spraying way of laying silicone insulation. Waterproofing on the platform should be drained additionally. Water may penetrate the surface and remain on insulation. At low temperatures, below freezing, it may freeze and burst asphalt pavement. We see it later in the form of numerous cavities on the road. The drainage consists of longitudinal drains, like the finished perco drain visible here, or the in-situ drain of geotextile and basalt grit and surrounded by an epoxy composition. In the vertical, water from the pavement is further removed by small filters with diameter of several centimeters, spaced approximately by every 3 meters. Here's an example of pavement surfaces with reinforced concrete slab decking. The same, but directly on a steel plate of the orthotropic deck. Here we have a railway track of a double track bridge made of pre-stressed concrete, but in curvature. That's why you can see the track tilt. Here's a rail ballast through on an orthotropic bridge with downhill ride. and also downhill driving, but on a pre-stressed concrete bridge. And here are fastening rails in the channels of precast panels. And finally, two examples of reasonable simple pavement on a pedestrian bridge. A steel orthotropic platform on deck on the left and a pre-stressed concrete structure on the right. Cross slopes and drainage location in the center of the deck are very characteristic. Now we'll briefly discuss drainage system. First, cast iron bridge inlet with a side outflow. The most crucial element of the drainage system is the outlets. You see them on the road surfaces. Their arrangement along the length depends on the longitudinal slope of the road on the bridge. The inlets are fastened at the lowest points of cross-section, most often at the carb. They can have a straight or diagonal connection to the main collector. Main collectors are also subject to elongation and shortening as a result of temperature changes, and this is done in a different range than a girder structure. Therefore, some exclusive compensators are needed here. Another group of components is related to the safety of users on the bridge. They are barriers and railings. They protect pedestrians, cyclists, as well as vehicles from falling off the bridge. Depending on the function of the bridge, they can only be used by pedestrians or cyclists, or additionally, can also reduce the vehicle's impact energy. We can also have combined solutions. According to current regulations, each barrier before its admission must be first checked in the failure tests on exclusive test tracks. Here you see an example of a bus. Uh, this is what the collision effects with a passenger car and a van looks like. We can see it also on the video. Now the same but with a bus. And truck with a semi-trailer. The previous tests succeeded, but this one unfortunately not. Balustrades are mounted on the outer edges of the bridge. It is designed for lower horizontal loads than energy-absorbing barriers. The height of the railings is 1.1 meters, and when moving bikes, up to 1.3 meters. The next group is expansion joints. They have undoubtedly been seen on the bridge many times, and maybe even hard when driving a car on the bridge. I'm sure that you could see it. Uh, these are elements that allow accommodating cyclic span movements caused mainly by temperature changes. Expansion devices are classified mainly due to the range of permissible displacements. So we have small ranges up to 45 millimeters, medium up to 130 millimeters, and large even up to 1 meter. Expansion joints must accommodate movements produced by concrete shrinkage and creep, post-tensioning, shortening, thermal variations, dead and live loads, wind and seismic loads, and as well as structural settlements. Many different solutions are used that adapt to the volume and type of traffic. Uh, they also differ in durability, noise, and of course price. Here we have the first two examples. Both is the cheapest and rarely used ordinary sheet metal, some plate, steel plate, which doesn't ensure full tightness. At the bottom there is a special elastomer insert, and is one suitable for pedestrian bridges where there is no heavy traffic. Two more examples. Above is a bituminous solution, often used for small movements, and below a modular solution with vulcanized bolted metal sheets. They are not used on highways. Bolts loosen quickly and can be dangerous for motorcyclists. However, this solution with steel profiles and elastomer insert is very often used on motorways. Besides, the patterns may have silencing caps. Here we have a multi-module version used for much larger displacements, for example, on long bridges or with terrain deformations. The last type is a finger device, which are used on the longest bridges. Another essential component is bearing, which unlike other devices shown today, it also used to transfer loads. Know them from mechanics, most often as fixed or movable bearings. They are a device between spans and supports. Their primary function is the transfer of loads in the form of reactions from spans to supports. Besides, they also allow relative displacements of the span relative to the support. Reactions are mainly due to self-weight, vehicle load, and wind or ground excitations. A movement can be caused by temperature changes and shrinkage and creep of concrete. We divide bearings into fixed and sliding ones. Constants, despite despite their name, block horizontal movement but allow rotation in all planes, and especially rotation resulting from bending of the span. Such restrictions are no longer limited by sliding bearings, although we can receive movements in specific direction. The bearing arrangement is of great importance in long bridges or with a large angle or curvature in the plan. We have many solutions used for bearings. The oldest is tangential, rocker, and roller bearings. Other types are lenticular, pot, and cheapest, but also the least durable elastomeric bearings. The last groups are devices and installations facilitating bridge maintenance and inspection. First, the usual stairs that the bridge inspector can go down under the span. Large bridges over inaccessible obstacles are equipped with individual platforms for inspection or repair of the structure. Another example of such a platform, but for an even more massive bridge located in Hong Kong. Many large bridges, especially suspension or cable-stayed bridges, are equipped with special vibration dampers for tendons and hangers, or even the entire span. We have already talked about this when discussing vibrations in footbridges. Electronic monitoring systems for technical conditions of structure are the most advanced at present. The largest and most responsible bridges have built-in hundreds of sensors that measure various physical quantities such as accelerations, displacements, deformations, temperature, wind loads, etc. They allow real-time observation of the structure's response to external loads. They can also help to identify the damages and make decisions about whether to close or need to repair the bridge. This completes the discussion of additional components for modern bridges. As you could see, it would be difficult today without these elements. And they are getting closer to what we will call in the future smart bridges. Uh, Thank you for your attention, and I'd like to invite you for the next lecture.